Always great to be back in Bochum, but I have a lot to say, so I'll jump right into it. So the main thing I want to talk about today is trying to understand new advances in reasoning, so-called reasoning models, and especially to investigate from a philosophical perspective, is that really reasoning? Because philosophers have tended to have a richer notion of reasoning that I think you often see discussed in this literature. But just to frame my work in this area a little bit, as Tobias was mentioning, I have a recent book that is about construing deep learning as a kind of empiricism in cognitive science today. If you ask the critics of deep learning what it is, they will tell you it is the latest reincarnation of behaviorism, right? So this is a picture of B.F. Skinner, and it's part of the founding mythology of cognitive science that you need to always check under your bed when you put your kids to sleep at night for B.F. Skinner's ghost, I guess, coming back generation after generation, right? And so if you listen to Gary Marcus, you see this quite explicitly, and he learned it from Pinker, who learned it from Chomsky. It's sort of very thoroughly in the DNA of cognitive science that you always need to be worried that empiricism is bringing B.F. Skinner back. My book says, no, actually no, there's very little in deep learning that fits this model. It's actually quite cognitivist. It's just a different approach to cognitivism, a thoroughly empiricist one. So there's 400 pages or so exploring dozens of case studies, looking at lots of architectures, DCNNs, GANs, variational autoencoders, LSTMs, and so on, and just show that what people are doing, even what they claim to be doing explicitly, is inconsistent with this simplistic behaviorist construal of deep learning. They really are trying to model significant structure inside the mind, significant representational processing, just not nativist or symbolic in character. So if you want to hear more about that, I could give whole talks on that, but I need to get to other stuff. So the book basically argued that recent advances in deep learning vindicate classical empiricism about the mind. So I think it's better to understand this in terms of like what John Locke or David Hume or William James say about the mind than B.F. Skinner. And they do so by modeling aspects of domain general empiricist faculties like perception, memory, imagination, attention, and so on. However, I did not in the book address higher or rational faculties like mathematical reasoning or deductive reasoning or planning. I kind of punted on that in the book because only recently, last couple of years, do we have models that can sort of reliably succeed at this type of performance. So that's what I've now, in the last couple of years, my work has turned towards these newer models to try to understand, do they also fit this model of empiricists cognitive science theorizing, and what can we learn from them about how we reason, for example. So the general orientation of the talk is I'll look at these new reasoning LLMs, or so-called LRMs, large reasoning models. Note that they're starting to show human-level performance on math and reasoning tasks. For example, both OpenAI and Google recently achieved gold medal performance on the Math Olympiad Challenge. And if that doesn't impress you, I sort of don't know what to tell you. But they not only got the right answers on novel math problems, but they even generated full proofs in language. And again, don't listen to Gary Marcus if you want to know what's actually going on. So that both Google and OpenAI claim to have done this entirely in language space. So these are not neurosymbolic models. If we're to believe what they say, of course, it's proprietary. They don't really let you look under the hood. But if what they say is true, these are not neurosymbolic models. They're doing it entirely in language space with the new reasoning tools. I think it's a live possibility that they achieve that performance by actually doing something worth calling reasoning, but that's a very long story that I couldn't fit in 40 minutes, and giving that story would involve a very wonky tour through LLM mechanics that we don't have time for. So what I'm going to focus on instead is scrutinizing the chains of thought that they produce in creating their answers. You know, they can self-generate 10, 20 pages of self-talk in text before they give you a final answer on these questions, and a lot of attention has now been placed on those chains of self-talk, or so-called chains of thought, to see if we can learn about the internal mechanisms driving their improved performance by looking at that text. And in particular, the computer scientists are already, there's a huge literature now studying, are these chains of thought faithful? That's the heading it goes under, and different measures of faithfulness. And so I'm going to scrutinize measures of faithfulness from a philosophical perspective and find them generally a little wanting and suggest some revisions that are more inspired by philosophy of mind. So I'm going to start by just mentioning briefly some of the gains in behavioral performance. Then I'll do a little detour through philosophy of mind. What have philosophers said about reasoning, and what insights might we take for computer science there? And then I'll talk about faithfulness, and in particular, I'll offer 4 new explications for different ways in which a chain of thought might be faithful to the underlying computations that produce the answers. And then I'll talk about ways to measure the more difficult notions of faithfulness using mechanistic interventions. So just very briefly, I'll kind of throw a whole bunch of data. So this is even GPT-4. Even GPT-4 was already doing very well on lots of performance tests for reasonings like SAT, GRE, AP tests, top human performance in many cases. But now the new reasoning models are doing really impressive stuff. So on novel math programs, this is from competition level math that you give to human undergraduates, it's getting 100th percentile, 96th percentile performance. And there's a bunch of examples like this I could show you just about performance gains. So I think everybody has to agree that by allowing these models to self-talk before they give an answer, you do get significant performance gains on a lot of the most interesting or important benchmarks for math or reasoning. However, I think it's good to remember one of the older thought experiments in philosophy of artificial intelligence. In particular, I like the blockhead thought experiment, so-called thought experiment from Ned Block back in the 80s. He said, imagine any time-limited conversation. There's a finite number of responses and counter responses that you could make. This was targeted to the Turing test of intelligence, right, where you're just engaging in a kind of dialogue to see whether something has intelligence. Now imagine you could hardwire an appropriate response to any question in the form of an extremely large lookup table. So the thought experiment was, imagine you had a very large government grant and you could hire all the domain experts in every subject area in the world and ask them every question, just get the right answer and kind of store it in a big lookup table. It would give the right answer to any question, but intuitively there's no intelligence going on, right? Block would say the intelligence there is the intelligence of the humans who gave you the answers that you put into the big lookup table. So the resulting system would pass the Turing test, but would it be intelligent? So it was targeted at the Turing test, but really it applies to any purely behavioral tests of intelligence, I think. So I think, actually, and I've argued with a co-author, Raphael Millier, in a couple publications, that blockhead-style memorization of right answers remains a very significant problem for all of deep learning performance metrics today, because they have such large data sets, and the data sets are largely proprietary, right? So we don't really know what the samples are that they've been trained on. Do we really know that they didn't sort of generate every possible variation of a Math Olympiad challenge question before they trained it? We don't. If you don't work at OpenAI or Google, we don't have access to these data sets and know what they've trained on or what they haven't. So I think at least, and this is not to say that everything they do can be construed as a kind of memorization. I think that's also known empirically to be false. But the question is, like, for any particular behavior that you see put up as an example, I think you can treat a blockhead-style memorization as a kind of null hypothesis that needs to be overcome with evidence. So in particular, there's technical results a lot of you in computer science probably know from Zhang et al. That showed that the memorization capacities of deep neural networks generally are much larger than we would have expected. So in particular, you can give them tens of millions of randomly labeled high-resolution images to a DCNN, for example, and it can just get zero training error, or nearly zero training error, on images where there's no patterns to learn to get the right answers. It's just memorizing piecewise the right label for each single data sample. And in large language models, there's also the lawsuit by New York Times against OpenAI where they showed that. Is there a problem with the audio?
I just think it's very loud.
That's what I thought too, yeah. Yeah, I told you I'm loud. Is that better? Thank you. Yeah, I know. I was telling him earlier I sounded like one of these booming heads on Star Trek that's talking to the ship or something. I was worried. Yeah, so as I was saying, we know that these things have a memorization capacity, like the New York Times article. Should I just take it off and talk?
I guess
Can you still hear me in the back?
What did you say?
You can use the other mic in the front here.
Yeah, we could.
This one. Just talk to that one.
This is muted now, so.
Time's ticking away. What do you want me to do here?
Okay, just try to speak through that mic.
Can you hear me like this? Okay, all right, I'll keep talking like this then. Maybe turn that one off. So yeah, like I said, treat memorization as a kind of null hypothesis that needs to be overcome with evidence. Either you have access to the data set or you do the right kinds of performance tests. And just to say this, giving a GRE or an SAT or whatever to these systems is not the most sophisticated version of a behavioral test. I think like Francois Challet's abstraction and reasoning challenge was built from the beginning to take this kind of worry into account. And he hopes through creating these really novel, maybe highly ecologically invalid types of tasks, that he can overcome the possibility of data contamination and memorization effects. I'm a little skeptical whether that really still works, because I expect what all the engineers are trying to do is create synthetic data sets guessing what Francois Challet did in the test train split. But set that aside. Even if we sort of succeeded in controlling for data contamination, I would still have worries about these as tests for reasoning, because they're still purely behavioral tests. And I think as far as philosophers and cognitive scientists more generally are concerned, they still wouldn't be well suited to assess reasoning. Because what do we want to know about reasoning? You know, these tests were designed to test something like general intelligence, if you believe such a thing exists, and maybe I don't. Or facility with human priors. Challet talks a lot about that. But it remains a purely performance-based metric. It can't assess things like internal representations, or algorithmic steps, or sensitivity to evidence, or internal confidence, or truth preservation across inferential transitions, or justification. And these might be things that philosophers and other cognitive scientists are more interested in when we start talking about reasoning. So the thought is we need to generally move beyond purely performance-based tests. So let's look at the new models with internal chain of thoughts. I'll give you a quick kind of primer. Susanna was talking about these yesterday, so I can maybe skip pretty quickly here. The long and short is we very early on with language models learned that if you ask them or prompt them to produce chains of thought before they give you an answer, then you get a big jump in their performance. So even just saying, let's think step by step, could produce in early models of GPT-3 like a 50% gain in accuracy on simple arithmetic problems. I like to think about this method generally. I'm an empiricist in terms of like cognitive scaffolding, right? So I think what you're doing is you're allowing the system to turn a difficult problem into a simpler problem by kind of gradually scaffolding it into a more similarity-based or familiarity-based problem. One example of this I like is counting letters. So you probably all seen on like social media, kind of embarrassing example from one of these systems that's supposed to be superhuman at something, being unable to count the number of letters in a phrase or the number of letters in a certain word. But I very quickly learned on that if you ask them to actually enumerate the letters in a numbered list, they almost always get the right answer, right? So I tried to get it to give a wrong answer, GPT-4, and it annoyingly got the right answer on the number of letters in automatopoeia and my name. Surely it hasn't been asked to count the letters in my name before, but set that aside. I finally got it to make a mistake. Where I am now in Florida, Gainesville is nicknamed Tree City, USA, because we have a lot of trees. And it finally got the wrong answer counting. But if you ask it to do a enumerated list of the letters, it pretty much always gets the right answer. And why is that? Because it turns it into a similarity problem, where all it has to do is look at what was the last number in the numbered list, right? It knows how to make a numbered list. It knows how to align letters with numbers on the list. And then all it has to do is read off 11 from the last number of the list. And I think this is a good model not only for how these systems can be bootstrapped to do more difficult reasoning planning type problems, but also how humans do it, right? I often make a point in my work, there's this area I call anthropofabulation, which is anthropocentrism about what's required to have a faculty, and then confabulation about how you actually do it. So if you ask me to count letters in a long phrase, I'm like wiggling my fingers or reciting numbers in my head, right? I don't do it sort of out of nowhere. I don't have an enumerator that can subitize letters up to 14. So this is just to point out, this is not a disqualifying factor for these systems that maybe they have to talk to themselves and change the problem into a different format to get the right answer. So the way these things probably work, again, a lot of the details are proprietary, but we've seen enough in publicly shared work that it's probably involves a kind of reinforcement learning on self-produced text where you get verifiable rewards. So you might have a theorem prover or a math checker or a code checker off to the side. And then it gradually learns to figure out what type of self-talk for me to produce for myself tends to get the right answer on this type of problem, right? So it's kind of a learning to produce adaptive kinds of self-talk based on the type of problem it's being asked to perform. Now, when you ask OpenAI, what do we get from these chains of thought, they say quite grand things. So they say, we can read the mind of the model and understand its thought process with this. They're also in this press release, they broke my heart and probably yours when they said, we've decided not to show the chains of thoughts to users Luckily, you know, DeepSeek came out not long after, and you can see the chains of thought there, so at least researchers have a tool to access these things without working at OpenAI. But there's still very grand claims. They read the mind of the model. Like, it's not only reasoning, but you can read the mind by looking at the chains of thought. And as a philosopher, I say, you know, really? Does it though? I mean, can we really, you know, trust at face value the chains of text as like a faithful report of what they're saying under the hood? This question is often posed in machine learning, is whether the chains of thought are faithful representations of the underlying computations the models perform to produce their answers. And luckily, philosophers and psychologists have thought about inner speech and human cognition and its role in reasoning for a long time, you know, going back to Vygotsky and even before in philosophy. You know, Plato, what is reasoning? It's the soul in dialogue with itself, and you can take that kind of literally in this case if you want. But it's controversial, even in philosophy especially, whether we think in inner speech, like we're scrutinizing the language of thought when we are aware of our internal monologue, or we think sort of with it as a kind of tool for scaffolding, like I was suggesting a minute ago.
Can you make a poll here?
What's that?
Can you ask how many people think in and how many ask with?
Well, that would be a metacognitive report, and we'd want to do empirical research to figure out whether that was accurate or not. I mean, some people also think in images, so there is individual variation there too that we know about. So that's also an interesting point too.
This because I assumed with would be correct.
Yeah, good. Yeah. Well, yeah, philosophers prefer the in a little bit more than psychologists. But let me get ahead before I get too far behind in the talk. We can come back to it in the Q&A. So when we ask this question of whether chains of thought can be faithful representations of model reasoning, I would say, but don't the blockhead-style worries apply? And this is kind of what I was raising to Susanna's talk yesterday. Don't they apply to the chains of thought too, right? So couldn't they be kind of just epiphenomenal memorization effects where it's just saying the kinds of things that from its training set it saw people say when they got the right answers on these questions, but it's not a faithful report of what that model is actually doing, because that could be a wholly separate process. If you look into the literature on faithfulness, there's a bunch of papers about it. They almost all cite this Jacobi and Goldberg 2020 paper when they characterized faithfulness. It came to be pretty influential. And that one was in turn adapting faithfulness from things like LIME, which we also talked about yesterday. You know, other methods of trying to understand what DCNN is doing, for example. And they just kind of ported that over and said, well, this will probably work for reasoning too. And that's where I want to say, whoa, 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 reasoning is a different kettle of fish. Maybe we want to slow down. So they give what they call the model assumption that a faithful interpretation should recommend the same decisions as the interpreted model. Okay. The prediction assumption that faithful interpretations recommend the same decisions if and only if, that's a little problematic, you'll see in a second, its reasoning is similar to that of the interpreted model, and what they call the linearity assumption, that some parts of a model's input are more important than others. So there have been some early challenges to the faithfulness of chains of thought, just to start to soften you up a little bit, where people wonder, are the chains of thought actually influencing the answers, or are they just kind of post hoc justifications or epiphenomenal side effects, you know, kind of like rationalizations you might find in human cognition, where we sort of tell ourselves that we're smart. You know, and it can go the other way too when this is maladaptive, right? So you can also, you know, have maladaptive chains of thought that are like unduly critical and lead to certain psychopathologies, for example. It's a common paradigm in the computer science to show unfaithfulness is to seed a fine-tuning set with an answer bias, like for example, give it a multiple choice test where the right answer is always A, and then you give it a test set and you see does it mention its answer choice by it when it then repeatedly chooses option A in the test set. And if it doesn't, you can say, well, I know there's a causal effect that's affecting its answers. It's not being mentioned in the chain of thought, so it's unfaithful to that degree. So, you know, here's an example. This Turpin et al. Gets a lot of citations. And you can show not only do the reasoning models, they're still subject to the answer choice bias. In some cases, it's even got a bigger effect in the reasoning models than it does in the non-reasoning models, right? So that might be cause for concern. And again, it tends to never mention the answer choice bias when it gives you the chain of thought. Yeah, and so, you know, this could be a problem for practical issues like safety and trustworthiness too, right? Because they can show that you can toggle, you know, protected characteristics like the race of a person in a vignette, where you know that's the only thing that's different between the two conditions. And if it changes its answer, but it doesn't mention the race of the person in the chain of thought, then you've got, you know, a protected characteristic that you know is being used to make a decision, but it's not being mentioned in the chain of thought. So that could be a major safety or trustworthiness concern. So, what are the issues with this Jacobi and Goldberg? Well, I just spent 400 pages in my book trying to tell everybody that deep learning is not behaviorist, but this is like an explicitly behaviorist measure of faithfulness, right? The idea is that all that matters for the faithfulness of the model is whether it's input-output equivalent to the decisions that the model actually makes. So it's, in other words, philosophers would call it a purely extensional criterion for understanding reasoning. It can't discriminate reasoning on the basis of two characteristics which are, say, conflated in the environment or extensionally equivalent, right? So philosophers love this example of creature with a heart versus creature with a kidney, right? So if you've got a circulatory system, you've got both. But according to this measure, you couldn't reason on the basis of having a heart without thereby reasoning on the basis of having a kidney too. But those seem like two different reasons to classify a certain instance. So again, this is issue with safety and trustworthiness considerations, because the whole problem of proxy variables is that these systems are so good at creating these kind of chimerical conflations of data that are extensionally equivalent to the protected characteristic in the data set, but then you're not supposed to be reasoning in those terms. So, there's little explicit discussion in general in this whole area as to what reasoning actually is. You almost never find in these papers somebody slow down and says, okay, so what is actually reasoning, and could we define it, and how would we know whether we're getting it here? So if we look to philosophy for a little bit of guide on that topic, reasoning is typically construed as being an intentional phenomenon, right? That means you can distinguish things like creature with a heart versus creature with a kidney. It depends on how the concepts are construed, conceptions, or how the evidence is taken, for example, which goes beyond mere behavioral input-output profiles. And I think this is a real worry in this case because we've got a lot of methods in AI speech which are all known under certain circumstances to be optimal, right? They all converge on optimal answers under certain assumptions, but they don't all use the same reasoning processes, right? So there's a lot of problems where you can show both an ANN trained on stochastic gradient descent and a Bayesian updating model will all converge on, the best answers to the problem, but they're obviously not using the same reasoning process to get there. Philosophers working on this area, they often emphasize the intentionality of reasoning by talking about a condition defended by Paul Boghossian, the taking condition, which says inferring necessarily involves the thinker taking their premises to support their conclusion and drawing their conclusion because of this fact. And so there's a kind of perspectivity in how you're taking the evidence to support what you're doing. Philosophers also typically distinguish explanatory reasons from justificatory reasons, right? And chains of thought could offer either. So the explanatory part is in part getting at this idea that you want there to be actually kind of a causal condition on whether you're actually giving an explanation for why the model gave this answer, what caused it to give this answer, as opposed to just something that's like a good justification for this answer that's independent. And rationalizations can be useful for that. And sometimes that's all you want, right? Sometimes all you want is a justification for an answer, and it doesn't really matter how you got to it. But when we're concerned about the safety and trustworthiness of the model, often we actually want explanatory answers and not just justificatory ones. Okay, so I'm going to do a little bit of an intermission here and review some work that's trying to figure out early on from an empirical perspective, what are the steps in the chains of thought actually doing? So there's, hypothesis one is a kind of very grand hope, and it's one that a lot of philosophers have had when they looked at this stuff, is that the chains of thought are chaining together semantically transparent pieces of evidence and inferential steps in a way that systematically respects logical form, right? So language of thought type people have sometimes gotten pretty excited at the chain of thought models and say like, oh, look, wow, we can finally see the language of thought. And they sometimes have this attitude towards inner speech and human cognition too, right? They'll say that is the language of thought. And you're thinking in these words, the position, a lot of philosophers defend this position, even if hopefully the psychologists are more skeptical. And I would say, at least in the AI case, this almost certainly isn't right. After all, there's still artificial neural networks under the hood, and there's all kinds of generic reasons for worrying that they're going to be able to learn perfect, kind of classical transitions in propositional form in inferences. But there's kind of an intermediate hypothesis that people have studied that's also still kind of interesting, and that's that they're chaining together islands of probability calculation that would otherwise be distant or inaccessible. I'll tell you what that means in a second if it's not getting there yet. But then there's also a super skeptical interpretation of the chains of thought that we have to take seriously. And that says that the text that's output is actually just irrelevant to what's produced. The chains of thought just allow the transformer more inference time computation before answering. So this super skeptical one the idea is that the problem with transformers as an architecture is there's no recurrent loops, right? So with RNNs, you could just keep processing on really hard problems, looping through until you sort of stabilized on the right answer. But most transformers don't have recurrent loops. So what the chain of thought lets it do is loop through text it's producing and just do lots and lots more internal computation before it gives the final answer. So it's kind of an indirect way for, I don't think this is a terrible hypothesis even about what's happening in human cognition when we do inner speech, right? You know, I'll say a little bit more about that in a second. But let's explore some of the evidence for these three hypotheses. There's a very nice paper by Prustowski, Lee, and Goodman. This is the hypothesis 2, that what chain of thought really helps it do. So if you're doing a hard generalization problem in machine learning, right, then you're asking it to evaluate the value of one variable on the basis of another one that have never co-occurred anywhere in the training set, right? That's a hard generalization problem. But what if the variable that is the target co-occurred with, you know, variable B and C somewhere, and then C co-occurred with E and F, and then F co-occurred with the seed variable that you're giving it in the prompt? Well, if you could chain together all those as like conditional probability estimations, then you'd have a more accurate estimate of the target variable on the basis of the seed one by routing through all the intermediate ones that did overlap in the training set. I hope that makes quick enough sense. And so they have a kind of analytical model for this based on conditional probability chaining, where they can characterize what they call the reasoning gap that, you know, is kind of roughly correlates with the performance benefits on the problems that they tested for when you test a chain of thought model, a reasoning model, versus a non-reasoning model, right? Where the idea is by producing all of those co-occurring variable sets from the training set in its chain of thought, it allows itself to give intermediate conditional estimates of all the intermediate variables and then finally inform the final one in that way. However, there's also evidence for the super-skeptical hypothesis that I mentioned earlier, that the text is strictly irrelevant. So for example, there's this paper by Pfau, Merrill, and Bowman where they trained it to just produce ellipses before giving an answer. And the idea is, because of the way self-attention works, into each ellipsis, it could just continually roll in more contextual information or steps in the problem and use that to do better computations of multi-step problems than if it was trying to do it sort of one shot or without any intermediate rerouting and performing more computations, right? So even just getting it to produce a whole bunch of ellipses until it gave an answer improved performance. There's another paper with a similar finding by Bengio and others where they, or sorry, Bengio's not on the, Goyal, where they just gave it silent pause tokens, and that also still improved performance. So the user doesn't even see them. It's just producing these invisible pause tokens, and it also improved performance. Now, the performance gain for the dot by dot and the pause tokens was not as big as you see in full chain of thought models, so I don't think this can be the whole story, but it's probably part of it. And yeah, if you look at human cognition too, right? So I don't know if you like train your graduate students not to say things like and yeah when they're presenting, but Dedeo and Berge studied the production of these filler tokens in human speech, in particular in terms of the information throughput of the text that they were producing before and after the filler tokens, and they found the humans seem to produce these tokens adaptively. That is, when the information content of their speech was dropping off, then they'd start producing filler tokens, and then you see the information throughput jump way back up after the production of the filler tokens. You know, so maybe, again, humans are doing this in part too. Okay, so another angle on which to study this is in terms of the qualitative strategies that the chains of thought are allowing these things to introduce. So these are things like backtracking to an earlier approach to try it again, or ordering different strategies for likelihood to lead to a success. You see this behavior sometimes too if you look at the long chains of thought. It'll say, you know, like, I mean, people made fun of it a little bit on this. Wait, am I going down the wrong path? Let me go back and try another one, right? But these are strategies that you can see in human problem solving too, especially as the problems get more difficult. So there's another paper by Goodman where they studied 4 types of these qualitative reasoning behaviors, trying to verify an answer, setting sub-goals, backtracking to an earlier strategy, and backwards chaining. And they also found that if you prompted models to do more or less of these strategies, you could improve reasoning performance on difficult problems, right? So this is part of the story too, is that they're doing sort of more macro level reasoning strategies that you can also see in human behavior, and that doing so improves the performance of the model. Okay, so here's kind of the new philosophical part. And this is work with one of my grad students, Arjun Krishna Kumar. So I say, well, when we've looked in faithfulness, we've just had this kind of simple behaviorist input-output equivalence criterion from the Jacobi and Goldberg. But what would we want if we were taking all this into account from both philosophy and the early empirical results on what the steps in the chain of thought might actually be doing? So the first one maybe corresponds to that grand goal. I call it syntactic faithfulness. And the idea there is that the syntactic structure of the sentences provided by the chain of thought reveal the formal structure of the underlying computations that the model performed to convert the input provided in its prompt to the output to deliver its final answer. But again, it's probably unlikely that, maybe, I will say that can sometimes be satisfied, but it's going to be a rare special case. The second is more corresponds to the kind of probability calculation model from Goodman et al. I call this configural faithfulness. So the idea there is that the chain of thought shows the model has categorized something as a member of a particular category, given a context-sensitive match between the target and the configuration of microfeatures that associates with the category, right? So these would be like the intermediate variables for particular properties that you can show are being assessed in the model. And these first two, just to note, they're intentional measures, right? They depend on how the evidence is actually being construed under the hood in the model. Then finally, there's the one that I think we're actually focusing on mostly right now, which is kind of behaviorist. I call it stimulus faithfulness. And this is where the chain of thought reveals which input elements were causally relevant to the production of the response to the query, but not necessarily anything about how those input features were construed or interpreted. But you would still fail stimulus faithfulness, for example, if you're influenced by an answer choice bias that you don't mention in the chain of thought. And the last one is a little bit different than the others. I call it strategic faithfulness. And that's where the chain of thought reveals relations amongst arguments in a chain of thought that were causally relevant to its production of O in response to Q, such as, again, backtracking, setting subgoals, or ranking candidate answers. Susanna was pushing me yesterday, which of these do I think is the right construal of faithfulness? I think it could be any, right? They're all important, and it really just depends on what question you're asking and what you're interested in, like what are your goals. I do think one is probably going to be only very rarely satisfied in large language models, though. Okay, so if you want to read a little bit more about philosophical debates about thinking in versus with language, there's this nice classic paper by self-professed radical connectionist O'Brien and Opie, where they go through lots of examples. This is just to kind of knock down why we shouldn't expect a syntactic faithfulness to be satisfied very often. Mashari is a little bit more on the nativist rationalist perspective, but he's also skeptical, like I am, that inner speech gives you the language of thought in which you're thinking, or that you can learn too much just by kind of the prima facie reading of what occurs in inner speech. So this is about inner speech in human cognition. Sententialism is the view that he uses for what I've called syntactically faithful inner speech, the idea that you're actually getting these kind of classical inferential transitions that you can read right off of your inner speech. And he argues against it, against what he calls the blindness of introspection thesis, where he says the fact that P is a property represented by a thought does not license per se the inference that the thought itself possesses P. So why would you believe that? Well, he gives a simple example of imagine a green triangle, right? Well, if you can picture a green triangle consciously, then you know you're representing a green triangle, but you don't know that there's anything green or triangular in your brain. Right? Basically, he says you have no idea what your brain is doing to produce the phenomenology of imagining a green triangle. And so similarly, just because we have these sentences in our head that are syntactically structured and have propositional form and so on, we know we're representing sentences and propositional form, but we have no idea whether the underlying computations that are producing that auditory phenomenology is respecting that logical form or propositional form, right? So for some reason, it's harder to think about in the sentence case than the green triangle case, but it's really the same inference. So this is really going back to the old debates between like Fodor and Polishin and Smolensky about whether you could have language of thought classically instantiated in artificial neural networks. And Mashari points out that the Lot story amounts to the claim that some mental formulas have mental formulas as parts, and those parts are transportable. That is, they can reappear in lots of other mental formulas, and they always have the same meaning in syntactic form. And there's just all kinds of generic reasons in LLMs, because they are these continuously differentiable artificial neural networks, why, especially if you think about how self-attention works, where you're modifying the vector value for each token in context, Like, why would you think that this semantic transportability condition would be satisfied for LLMs when every token and every residual stream is always being informed by the particular context in which it appears? And crucially, we can't infer from the fact that we process these sentences sententially that the LLMs do too. In fact, again, the holistic context dependence of self-negation speaks against this. Okay, so for the first two notions of faithfulness that were intentional in character, we might now ask, is there any way for us to actually measure the intentional faithfulness of the chains of thought that we've produced when we're looking at these models? I just want to point out that simple linear decoder methods, which are all over the place, they're not going to be sufficient. Why? Because they just show that the information is present in the model, but they don't show that it's actually used to generate the answers, right? So to illustrate this, I give a simple example. Suppose I'm visiting my cousin's house in the suburbs, and they have this really obnoxious live, laugh, love decoration that always annoys me every time I go over for coffee or a beer. And one time when they leave me unattended for too long, I take it and I throw it in the pond in their backyard, and it sinks, right? Imagine it's heavy, so it sinks down. But my friend is in AI, so he uses a linear decoder method to decode which letters were producing the ripples on the surface of the pond, which he can do, right? Because there's a particular pattern in the ripples that the linear decoder method can pick up the information as to which words were thrown in the pond. But that doesn't mean the pond is computing the words, right? It doesn't mean that it understands anything about letters or letter order or anything like that. It just means the information is present in the pond's surface ripples because they perturbed it in a certain way. And I think we have the same worry for linear decoder methods applied to LLMs. So for example, you show an input to a human and you show an input to an LLM. Well, those are very highly complex inputs with lots of information. They're going to perturb the activations of the model and the human brain. And then you show, oh, look, well, we've got high linear predictivity from the model activations to what happened in the human brain. But you haven't shown that the model actually uses that information to do anything. So that's just the critical point. In order to do that, you actually have to do mechanistic interpretability work, right? That's where you look inside the model and you actually muck about with its internal activations, for example, move them around in hypothesis-driven ways. Ablation is the easiest form, and there was a little talk about that yesterday. But now we can also do more sophisticated forms like activation patching, where you're moving the vector for some particular thing in a hypothesis-driven way to, say, toggle an attribute. How am I doing on time? Maybe I'll just give you one example. Yeah, I better give you just one example. Yeah, we lost like 5 minutes for microphone stuff. So I'm going to give you what I call Buckner's repugnant conclusion here. For any sufficiently large and complex model that's trained to find its own solutions by configuring a whole bunch of simple components through gradient descent learning, you can't answer any philosophically interesting questions about them without actually gathering evidence of its acquired representations and causal organization. Sorry, philosophers in particular in the audience, we have to get our hands dirty with empirical work here. In particular, interventionist interpretability techniques, which I'll talk about shortly, are the most promising avenue. So I'll give you one quick example. I'll skip this one. One that's really easy to see in the linguistics case is by Linzen and Refogel, linguist and a computational linguist. So they were interested in seeing if they could provide interventional evidence that these models represent a particular grammatical property and actually use it to generate their outputs. So for example, they could focus on relative clause membership. And so what they did is they ran a linear decoder and they found a direction in activation space that seemed to correlate, have information about relative clause membership of words, right? And so then what they can do, and this is called iterative null space projection, is you take that subspace where over here you've got information about the word being in this clause, and over here you've got information about it being in the other clause. You can take the sentence's vectors and just project them across that subspace, like a mirror image across that subspace, where the idea is you're preserving all of the other semantic information in the sentence, and you're just sort of toggling this one grammatical property. And then you see what completions does the model then go on to recommend. Does it now toggle as though if you've negated or flipped it to being a member of the other clause, does it now act like the word is a member of the other clause when it's doing its grammatical completions? And this is just one example. There's lots of other examples, not in a purely linguistic domain. You can do it with world models, where if you think you have located a world model that you think the model is using to inform its predictions, you can say take its internal activation for property A and property B over here, and you can sort of paste the value, this is activation patching, of property B in this context to property A, and then say, oh, does it now act like property A has what was previously the value of property B, even though that's inconsistent with the prompt it was given. And the idea there is that this is kind of representation editing. It shows not only that it was representing the thing that you thought it was, but also that it's playing a causal role in generating the outputs. So if you had an intentional hypothesis, in other words, from the first couple notions of faithfulness that I discussed, you could then toggle it using activation patching, for example, and then use that to kind of confirm your faithfulness measure of the way that you were construing the chain of thought in the model. Yeah, I'll skip ahead. So if you want to get into this, there's great work by this group at Stanford, in particular Atticus Geiger and Thomas Eichhardt's a philosopher. They've even kind of generalized this into a method they call causal abstraction, where you build kind of a causal diagram of the whole flow of variables you're hypothesizing occurs in this network, and then you do systematic so-called interchange interventions where you're toggling all of those properties in hypothesis-driven ways and seeing if it affects the modeled behavior in the right way. And the thought is that gives you a kind of interpretable diagram that's been verified with interventionist experiments on the activations. I have a review of this with my co-author, Raphael Milliere, that's also kind of from a more philosophical perspective. If you want to get into this, you can find this easily on arXiv. Just to end a little bit, there are, I think, limited cases where we might get close to something like syntactic faithfulness that I kind of suggested would be rare. So I don't know how many of you looked into the sort of grokking cases where there are sometimes in the double descent where you train large language models well past kind of the ceiling of training error. Sometimes you see a kind of dip back in the double descent, right, of generalization error, and then sudden jump again in generalization performance, where now it's like almost getting the right answer even on the most difficult generalization tests. One example that was studied by Nanda et al. Was on this addition thing where it really seemed to learn a really generalizable algorithm for doing addition. And they did very careful circuit interpretability work where they found it was doing an algorithm that was known to humans. It's something very close to this heuristic for doing addition called modular addition, where you pick a modulus and then you have a number of circles that go around the modulus. So for example, if the modulus is 10, then a full way around the circle would be 10. And you can do this with vectors in vector space is the key idea, right? So you can, every time you go up one, you move the vector around the modulus there, and every time you go all the way around, you move to the next circle and you start the modulus there, right? And you can get exact answers to arithmetic problems entirely in vector space by using this kind of modulus, and there's nothing wrong with it, right? But the problem is the chain of thought is probably not going to mention modulus and going around circles in vector space. But if it did, then I think you would have a case of like real syntactic faithfulness. It's telling you not only that it's got a fully syntactically adequate solution to the addition problem, but it would be telling you faithfully how it did it. How we get the models to actually be that faithful, I don't know, but it's possible is all I'm saying. Okay. So that's the main story I wanted to tell. The takeaways are it's going to be very difficult to assess large language models as models of human reasoning on the basis of behavioral performance tests alone. And that's because, again, reasoning should be understood as an intentional phenomenon. And the reasoning models that we've got here seem to succeed by recapitulating approximate properties of classical computational models, but it's almost never by using explicit symbols or rules or innate domain-specific programming, and they rely more on scaffolding that they can use to, say, convert logic or math problems to similarity-based inference problems, or, for example, like I was just saying, problems that can be done in kind of vector space easily. So I think this is more of a victory for empiricism, just to say, you know, we're really getting to the highest reasoning type stuff, and there's still not the classical machinery that they always said we need under the hood. And I think mechanistic interpretability techniques are going to be the best route to assess intentional forms of faithfulness. But just buyer beware. These methods are very new. They're only a couple years old, and we sort of don't know what their capacity for false positives is. So this is a new area of research, I think, for us to be skeptical consumers of these new methods. Thank you for your attention. There's time for questions, I hope.